All right, so in this part of the chapter, we're going to be taking a look at a property of substances known as their specific heat, or sometimes called the specific heat capacity. And sometimes this is abbreviated as SH for specific heat, or in a much more concise way, you'll see it being represented as C, lowercase c. And we'll talk about where we see that in some equations in a little bit. So what exactly is the specific heat? Well, we can define it as the amount of heat needed, and heat can be measured in joules or calories. So the amount of heat that's required to change the temperature, usually to increase the temperature, but also it can be the amount of heat that's lost when the temperature of a substance changes by 1 degree Celsius for 1 gram of that substance, right? So we say the specific heat, the amount of heat needed, either in joules or calories, required to change the temperature of 1 gram of a substance by 1 degree Celsius. So if we kind of use units to help describe that, what we end up seeing now, the units that we typically see are joules, the amount of heat per gram degrees Celsius, or calories per gram degrees Celsius, right? So those are the most common units that you'll see depending on whether you're looking at the SI system or the metric system. So different substances have different specific heats, as you probably could guess, but what exactly does the specific heat really tell us? Well, it gives us an idea of how quickly or how slowly a substance is actually able to warm up or cool down. So if you look at it from a different perspective. So it gives an idea, it gives us an idea of how easily or how quickly a substance warms up, and conversely how easily it cools down. Okay, and I'll just give you the sort of the take-home point here right now. Substances with low specific heats or small specific heats warm up very quickly, and again we can also say cool down. And then conversely, we can say then that substances with high specific heat or large specific heats warm up or cool down very slowly. So in other words, substances with high specific heats, you need to provide a lot of heat energy to increase the temperature of 1 gram of that substance, whereas substances with low specific heats, you really only need to provide a small amount of energy to increase their temperature. All right, and we'll take a look here at some of these terminologies that we'll see in our heat equations. So we'll just jump down here really quick and take a look at some examples of specific heats for different substances that you may encounter on a regular basis, and we'll try to make some sense of these numbers, but also try to maybe apply it to what you already know. So let's just focus on one of these columns. It doesn't really matter which one. We'll just choose the let's choose the joules per gram degrees Celsius, and we'll just compare those numbers to each other. So if you look here in the top half of this table, we have aluminum, we have copper, gold, iron, silver, titanium. Those names should sound familiar to you. These are all metals. right? And in your personal experience, what you probably have noticed is that metals, when they're exposed to heat, right, they're able to become hot very, very quickly. So these become very hot very quickly, which is why, you know, we use metallic pots and pans for cooking, right? So when exposed to heat. So that means they warm up very quickly. And as a result, right, we can predict that they should have a low specific heat. And all of these, you look at their numbers, they're all less than 1 joule per gram degree Celsius. So they have very low specific heats, which is kind of what we introduced at the beginning of this talk. So low specific heats. And if we compare those, the specific heats for the for these metals to something that we're very familiar with, and we'll just choose water here, liquid water. And you can see that its specific heat is much higher, relatively speaking, than all of those metals. Right? So water, liquid water has a much higher specific heat than the metals, in other words. So what that suggests then is that water will warm up slower than a metal, like the ones listed above, like a metal, when both are exposed to the same amount of heat. All right, and we can take that and apply it, that idea of what specific heat is, and apply it to something that you may encounter or that you may experience on a maybe not a regular basis, but you probably have seen this on TV or experienced it on your own. You go to the beach, all right, in the middle of the summertime. It's very hot. You go down to Houston or on the coast, the Gulf Coast, for instance, and you have your sun. So this is our sun up here in the sky, all right, and it's producing a lot of heat energy, and it's shining down on both the ocean over here on the left side. So there's our ocean, and then the land here, or the sand here on the right. All right, so both the ocean and the sand are being exposed to the same amount of heat energy from the sun, yet when you go to the beach, all right, what you notice is that the sand, relatively speaking, is hotter than the ocean, which is cooler. So how can we explain that in terms of the specific heats of both of those things? So because the sand gets hotter quicker, we can predict then, based on what we just talked about from that table, we can predict that the sand has a lower specific heat than water. So it takes a very small amount of heat energy to increase the temperature of the sand, so it feels very hot. Whereas the ocean, which is made up of water now, has a higher specific heat than the sand. All right, so even though it's exposed to the same amount of heat energy, its temperature doesn't increase as much, and as a result, it feels cooler than the neighboring sand. All right, and you know, when you go to the beach in the middle of the summertime, you step on the sand with your bare feet, it's burning hot, and you jump in the ocean to relieve that pain that you feel in the bottom of your feet. That is chemistry in action. All right, that's the difference in specific heat of both of those two things, the sand and the ocean. So let's take a look now at how we can put some numbers behind that qualitative description. And when it comes to the heat problems, what we're going to use in these heat problems is an equation called a heat equation. And we'll just define that heat equation here. So the heat equation and you'll see lots of questions on your study module, on your homework, based on this heat equation. So the heat equation goes like this. The amount of heat needed or produced is equal to M, which is the mass, times the specific heat, times the change in temperature. All right, so there are some symbols that we use for these things. Heat is often referred to as Q. Mass is M. Specific heat is often referred to as SH, or sometimes it's just referred to as C. And then the change in temperature is abbreviated as triangle T. And what this triangle is read as, it's called delta. So delta T. All right, and whenever you see delta, that means change in something. All right, so our heat equation essentially now is Q is equal to M times C times delta T. And these little dots that you see here, you can think of that as meaning multiply. That's a quick way by which we represent the multiplication. All right, so Q, which is the heat, is equal to the mass times the specific heat, C or SH, times delta T, which is the change in temperature. So when you're given an equation, or sorry, a problem involving heat, we can use that equation, and then we should be able to do a little bit of algebra on it too. Okay, we should be able to rearrange this, so we should be able to solve for any unknown in this equation. Right? Oftentimes it's the heat that we need to solve for, but in some cases it could be any of these other three things that we need to determine. All right, so with any question, you want to make sure that you approach it, systematically, and you sort of list everything you're given, and then hopefully you'll see that there's only one unknown that we need to calculate. All right, and in some cases it's pretty obvious from the question what they're asking you to do. So here it's saying, what is the specific heat? So right away, all right, we know that we need to calculate the specific heat, SH, or just C, of lead, and then tell you the units that we're going to calculate. If 57.0 joules, all right, so you have to recognize this as heat. Joules is a unit of heat energy, raises the temperature of 35.6 grams, that's a unit of mass, by 12.5 degrees Celsius, right? That's the change in temperature. Okay, so what are we given in this problem? Well, we're given the heat is equal to 57.0 joules. We're given the mass is 35.6 grams, and we're given the change in temperature, delta T, as 12.5 degrees Celsius. What do we need? All right, we need to calculate the specific heat, SH, or just C. So what are we going to use? Okay, we're going to use the heat equation. All right, and I often abbreviate equation as EQN just to save on time, to be a little lazy. So our heat equation, Q, which is the heat. Again, heat is Q. Our mass is M. So Q is equal to M times C, our specific heat, times delta T. We need to calculate the specific heat, or C. So if we rearrange our equation, we do a little bit of mental gymnastics on it, right? We end up with C being equal to, we move everything else over on the other side. You have to divide the left side by M and delta T. So we end up with Q over M times delta T. And all we need to do then is to substitute our values that were given in the problem. So we have now our C is equal to Q, which is the heat, up here, 57.0 joules, divided by M, our mass, 35.6 grams. Okay, and that's multiplied by our change in temperature, delta T, 12.5 degrees Celsius. All right, and then all that's left to do is to stick that in your calculator. And what you would see is that your specific heat ends up being a relatively small number because, again, if you look at it, it's lead, which is a metal. We would expect it to have a very low specific heat. And then our solution down here, we get 0.128 joules per gram degrees Celsius. So 0.128 joule per gram degrees Celsius. So really, you know, what these problems boil down to, again, and you probably have heard me say this multiple times, is just math that you're doing, but we're applying math to chemistry. All right, so the key thing here is to know what we're using. We're using the heat equation, all right, which is this equation, and then we can rearrange it to solve for any of our unknown in that equation, which means you need to take a close look at your problem, the problem that's given, and identify what you have and what it is that you need to calculate.